Welcome to this explainer. Today, we're taking a deep dive into Chapter 3, specifically looking at immunopathology and amyloidosis. We're going to trace the entire journey from the incredible microscopic mechanics of a perfectly healthy immune defense all the way down to some pretty complex systemic failures. If you've ever wanted a clear roadmap of how the body protects itself and, exactly what happens when those defenses go totally awry, you are absolutely in the right place. Let's get into it.
So, here's our roadmap for today. We'll start off with the immune system basics, then look at what happens when immunity goes wrong. After that, we'll shift gears to really understand amyloidosis, and finally wrap up with how clinicians actually diagnose and track it.
All right, Section 1, the immune system basics.
Now, our immune defense literally relies on infrastructure and personnel, right? To truly get immunopathology, we first have to respect the healthy mechanics. We've got dedicated organs functioning kind of like military bases, places like the thymus, the spleen, and lymph nodes, where our immune cells mature and mobilize. Then we have the specialized cells themselves, like T cells and B cells. These are basically the microscopic soldiers doing the heavy lifting to neutralize threats. But having millions of cells scattered throughout the body just isn't enough. The need to act as a unified force. And that is exactly where cytokines come in. You can think of cytokines as the body's high-speed chemical alarm system. The absolute second an invader is detected, these proteins are released to instantly coordinate a massive targeted response, basically signaling all those immune cells to rush straight to the site of the infection.
Now, right at the center of this defense network is the HLA system and the Major Histocompatibility Complex, or MHC. Think of this as the body's ultimate security checkpoint. Basically, every single one of your cells has a unique molecular barcode right on its surface. The MHC is this complex mechanism that allows your immune system's patrol cells to scan that barcode and make a split-second determination. Are you friend or are you foe? If the barcode matches, cool, the immune cell moves on. If it doesn't, the cell sounds the alarm. This microscopic ID system is literally the bedrock of our everyday survival. It ensures we fight off foreign invaders while totally leaving our own healthy tissues in peace.
But here's the catch. This system's ruthless efficiency can absolutely become a double-edged sword. A normal, healthy system peacefully accepts its own tissue because, well, the barcodes match perfectly. However, in the case of a life-saving organ transplant, this exact same mechanism causes an incredible hurdle. The recipient's immune system sends out its patrols. The MHC scans the new organ, realizes the barcode doesn't match the host, and instantly flags that entire organ as non-self. This triggers a massive, destructive immune attack. It's this tragic biological irony, really. The very system designed to keep us alive will relentlessly attack a transplanted organ that's trying to do the exact same thing.
Which brings us to Section 2, diseases of immunity.
This raises a pretty terrifying question, actually. What happens when our ultimate defenses completely collapse? How do diseases manifest when the highly coordinated system that's supposed to protect us from harm fundamentally fails to do its job?
Well, these biological failures generally fall into three massive categories. First up, we see complete system collapse. This is represented by acquired immunodeficiency syndrome, or AIDS, where a virus specifically targets those command and control immune cells. It effectively wipes out the defense forces, leaving the body totally defenseless against otherwise harmless microbes. Second, we have hypersensitivity reactions. Think of these like severe, life-threatening allergies. It's an overactive, panicked immune response to a harmless substance that ends up causing catastrophic collateral damage to our own tissues. And finally, autoimmune diseases. This is kind of the ultimate betrayal. That friend or foe barcode scanner we just talked about, it breaks down entirely, and the body tragically wages war on its own perfectly healthy organs, treating them as dangerous invaders.
Moving right along to Section 3, understanding amyloidosis.
To really grasp this specific disease, we have to look closely at its unique chemistry. You see, amyloidosis isn't caused by some foreign virus or a replicating bacteria. It's actually a disease of rogue proteins. Normal proteins in our body are pliable, perfectly folded to do very specific jobs, and easily broken down and recycled when they wear out. But amyloid proteins? They have a severely abnormal structural makeup. They are misfolded, rigid, and incredibly stubborn. Because of their corrupted shape, they form these tough, insoluble sheets that the human body just literally does not know how to dissolve or get rid of.
So the pathogenesis, or the step-by-step origin story of the disease, follows this relentless compounding cascade.
It starts with the formation of precursor proteins. These are often produced in excess because of underlying inflammation or bone marrow disorders. Now, because there are so many of them, or maybe because they're mutated, these proteins undergo that dangerous misfolding process we just mentioned. At this point, the body's microscopic cleanup crew comes in to clear them out, but their tools just bounce right off the rigid amyloid structure. As a result, these indestructible proteins eventually just deposit and stack up in healthy tissues like cellular garbage. And over time, these growing mounds of protein slowly crush the native cells, completely disrupting the function of vital organs.
Now, because there are different types of precursor proteins in the human body, amyloidosis isn't just one single uniform disease. Clinicians actually use a really precise classification system that groups amyloidosis by its specific chemical type and directly links it to an underlying condition. For instance, some misfolded proteins, like AL amyloid, originate in the bone marrow and really prefer to deposit heavily in the heart and kidneys. Other types, which might be driven by chronic inflammation, might target the liver or spleen instead. Organizing the pathology this way isn't just an academic exercise, you know. It's absolutely crucial for diagnosing the root cause and predicting exactly how the disease is going to present in a specific patient.
And that leads us to our final part, Section 4, Diagnosing and Tracking Amyloidosis.
Diagnosing amyloidosis actually requires some highly specific laboratory techniques. Why? Because to the naked eye, and honestly even under standard magnification, these proteins just look like pink, formless material hiding out within normal tissue. So, to secure a definitive diagnosis, pathologists rely heavily on unique tissue stains. The most famous, and definitely the most crucial of these, is the Congo red stain. When this specific dye is applied to a tissue biopsy, it binds tightly to the rigid structure of the amyloid proteins. And then when a pathologist puts that stained tissue under a special polarized microscope, something pretty incredible happens. The hidden amyloid actually lights up with this brilliant, unmistakable apple-green glow. It finally reveals the invisible culprit.
Once that diagnosis is secured, clinicians have to evaluate the morphologic features. Basically, that means looking at the gross, physical, visual, and structural changes to the organs themselves. Like we discussed, these misfolded proteins can't be broken down, so they just keep piling up. The sheer, overwhelming volume of these deposits physically alters the architecture of the tissues. The affected organs don't just fail, they literally change shape. They often become massively enlarged, incredibly heavy, and stiff, taking on this pale, waxy appearance. This literal physical overcrowding suffocates the native cells, completely robbing the organ of its flexibility and its ability to function normally.
Ultimately, wrapping your head around this disease comes down to the prognosis. Because the body inherently struggles so much to clear out these indestructible protein deposits, the disease progression is often just relentless. Without aggressive medical intervention that specifically targets the underlying condition to stop the production of those precursor proteins, these toxic deposits will simply continue to accumulate. Over time, this leads to severe, irreversible, and often fatal organ failure, particularly if the heart or kidneys are heavily involved. It's a sobering but absolutely essential reality of clinical practice. And honestly, it's exactly what drives researchers to find better, faster treatments.
So, as we wrap up, I want you to keep this delicate, sometimes really dangerous balance of the human body in mind. How can the very system designed to keep us alive be the exact same system that brings about our undoing? From the tragic irony of transplant rejection to the self-inflicted wounds of autoimmune diseases, all the way to the microscopic garbage pileup of amyloidosis, it's a profound, kind of chilling thought to carry with you as you explore the incredible complexities of immunopathology. Thanks for joining me on this explainer, and as always, keep questioning.